on time, you know why.
Just
Just trying to be nice. Okay, so today we're going to be talking about the first part of probability, so not random variables and geometric and binomial. The stuff that are like tree diagrams, Venn diagrams, all of that little stuff. Okay, and hopefully if we get through, we can look at the tennis question in 2000, like the practice exam. Remember that one?
Oh, yeah.
Player V and player M. Okay, so that's the plan today. All right, so I'm not going to spend forever on this part, but hopefully sometime I'll find a quick minute to do an example of this because I feel like I've added you to death the past couple of days. So I figured you knew ads. Just remember that for simulations, we tweak ads just a tad. So remember that as you're going through ads, there are a couple other things you need to talk about. What is a component? So what that means is, as you're going 2 digits at a time, what do those digits represent? Does it represent drawing a gift card? Does it represent opening an oyster? Does it represent, I can't remember all the simulations we did, but you know what I'm talking about? Like what does it represent? What is a component? That's the vocabulary word. And then you also, as you're working through ads, need to make sure to define a trial, meaning how do I know when to stop? Okay, do I stop after I draw 10 gift cards? Do I stop after I get 5 oysters opened? Or do I stop after I get 5 pearls or whatever, you know? So tell the reader when a trial stops. The third extra thing that you need to do with simulations is make sure you define the response variable. So after you stop in a trial, what are you recording? What are you measuring at the end? Are you measuring the total amount of gift card values that you had? Or are you recording how many pearls you got in the oysters that you opened? I'm only using those as an example because we did those examples a long time ago. Okay, so that's the 3 extra stuff in addition to ads when you're doing simulations. The component, define a trial, and define the response variable. Now, do y'all remember when we actually had to perform the simulation? We had to they gave us a little sample of table of random digits and we had to mark on it. Okay, so mark on it, feel free to. Remember, at the end of a trial, we do what?
Draw like the line.
Yeah, there's a little bar, right? A little bar, we draw that bar, and above that bar, we write the response variable. Okay, so what do we figure out? What do we figure out at the end of this trial? Okay, and you write it there. Usually they say do 3 trials or something like that. I think I made y'all do like a ridiculous 20 or something one time.
So we do like 3 out of 5 for the response variable.
So it depends. So sometimes, if you do 5 trials, maybe 3 of those trials you got oysters. So your answer for step 3 would be 3 out of 5. But maybe for your maybe you did 5 trials and you did quantitative data. So you got $100 gift card in this trial, and then $250, and then $25. Maybe I need to average those. So it kind of depends on if it's quantitative or categorical data, what your final step is.
So for the response variable on the bars, you just write yes or no?
No, the response variable is what are you recording after a trial is over?
So number of whatever.
Good. And then step 3 is taking all of your answers, what you're measuring at the end, and making some kind of conclusion. Good. So I'm hoping to maybe find a chance here or there to do one of those together just really quick. But I'm not, since we've ads all week this week, we'll save it maybe for next week. Let's get into probability. Okay. Just some rules, some formulas. Just jumping right into it. The capital letters are events. Okay, that's what they're called. That's what they're representing. Events. So flipping a coin, rolling a die. That's an event. Okay. So the complement rule. That's that little C. Okay, and that just means the opposite of A. So if I say that A happened, the complement would be A not happening. Okay? So to figure that out, you just do 1 minus that probability. The addition rule. Okay? This is on your formula sheet. You don't have to memorize it. You just need to know when to use it and how to use it properly. So, can y'all remind me of these symbols? So, what's
One's
this
and,
little U
one's
looking
or.
one?
That's or.
That's or. Very good. And then what is this one?
And.
And. Good. Okay. So, why do we have to? Because when you think of or, you should be thinking of addition. And when you think of and, you should kind of be thinking of multiplication. Okay? So, how do I, why do I have to subtract out an and? Very good. If you remember Venn diagrams, yeah, exactly. If you remember Venn diagrams, that's large. Let's make that a little skinnier. Okay. Okay, if you remember Venn diagrams, that's pretty.
It's a Venn diagram.
It's a little hard to draw with a mouse, okay? Okay, so what is happening here is you do the probability of A, and then you do the probability of B, but what happened when I did that?
You included in the middle.
Counted the middle twice, so I have to subtract it out. Okay?
So A or B is A or B or both.
Yes. Okay, good. So let's practice. Speaking of Venn diagrams, let's practice them. Okay, so I have two events. These are like dealing with cards. So I have two events, getting a face card and getting a heart. That's right. Okay, so you got to know your cards. What's a face card?
Jack, Queen, and King.
Jack, Queen, and King. So if I draw a card at random, what's the probability of getting a face card?
12, 6.
I agree with 12. Why 12?
Oh,
3 times 4.
Yeah. All fours. So, I guess face card is King, Queen, Jack, and then there's 4 of each of those. Good. What's the probability of B getting a heart?
1/4.
A fourth, but how many out of 52? I like to keep the bottoms the same. Yeah, 13 out of 52. Okay. And then what's number 3 say?
A and
Probability of getting a face card and
Good, face card and a heart. So you kind of have to use your brain. How many face cards are hearts? 3. Good. The Jack of Hearts, Queen of Hearts.
So that's
It's more of a struggle.
You need to study a deck of cards.
Yeah, maybe
It's
you need
more
to
of a
do
struggle
that.
than the probability.
What did you say, Jake?
never mind. I'm sorry.
Okay, this is the 3 pieces of information you need to make a Venn diagram. Okay, so one of the questions, how do I know when to use a Venn diagram? It's when you have probability of A, probability of B, and then the probability that they both happen. Then it's setting you up for a Venn diagram, and then they're probably going to ask you something like 4, 5, or 6 after they give you all that. So this happens on multiple choice questions a lot. Okay, what's the key? Where do I start? Middle. Always start in the middle. So what should go there? 3 out of 52. You got it. So then, what should I write under A?
9.
Why 9?
because it's 12 minus 3.
Good. We gotta subtract out.
12 minus 10.
We gotta subtract out the middle.
It's pretty impressive.
Because if you, I know I'm trying really hard. If you look at all of A, which includes this whole entire circle, you're looking at 12 out of 52, which is our answer to 1. So what should I go under B?
10.
10. Good. At least the math was kind of okay with this. Good. What goes on the outside?
The remainder.
52 minus.
So 9 and 3 is 12. 12 and 10 is 22 out of 52. But subtract from 1. 30. You got it. Now I'm ready to answer anything I want underneath here. 4, 5, or 6.
Could this be a short answer?
It could be a short answer. I haven't seen it very often because they're not very interesting. They can't, but yeah, too easy. So I've seen it mostly as multiple choice. All right, how do I find the probability of A or B?
Probability of A and the probability of B minus the probability of
Okay, so Saria is quoting this right here, the addition rule, which is fine. Okay, you can use this addition rule, A or B, which has the probability of A plus the probability of B, subtract out the overlap. But be careful, is 9 over 52 the probability of A?
No, it's
12 out of 52 is the probability of A.
So can you just do 9 plus 2 plus 10?
Right, so there's two ways to do this. You can use the formula, which means 12 out of 52 plus 13 out of 52 minus 3 out of 52. That's the formula. But what's using the Venn diagram? Nita, you were just saying it.
9 plus
9 out of 52 plus 3 out of 52 plus 10 out of 52. That's kind of the shorter way. Just go straight across. Because the reason why, we've already subtracted the overlap when we
And
made
it's
the Venn diagram.
Remainder of the.
Wait, why do you add the overlap? Why don't you just do 9?
Because technically it's A or B or both. We just don't see the or both part. So our answer would be 22 out of 52. Alright, the probability of not A.
40. 52
Anything but A.
minus 12. 48.
Yes, 40 out of 52. So it's 1 minus A. That was our complement rule. So if A is 12 out of 52, this will be, or getting a face card, this would be not getting a face card, which is 40 cards out of 52. Opposite of 12 out of 52. What's 6?
And not B.
A and not B, which means what? A occurs for sure, but B doesn't.
So 9 out of 52.
Which one is it?
39. No, it's 9 out of 52.
So I see what you're thinking when you think 39, but A happens. Okay? So we know it is this part right here. Because
We're
out
on
here,
12.
A does not happen.
Oh, B doesn't have it at all.
B doesn't happen at all. A definitely happens, so it is 9 out of 52. Good. All right, what about the last one?
30. I'm kidding.
30.
Yep.
Oh,
So neither A nor B happens, so
You said 30. That's like I'm saying.
30 out of 52. So what is the complement of neither A or B? Careful with your wording.
A or B.
A or B. Good. Because, so these two are complements of each other. Neither happening or A or B happening. So, good. Those are complements of each other. Good. So hopefully that will help you get a multiple choice question right. Or maybe you'll get lucky and it'll be a free response question with this. That would be nice.
Dog live in the house.
Yeah, that would be good. Just remember when you're making it, start in the middle and subtract. Cool? All right, the multiplication rule. So there is like technically a formula, but I really just don't suggest worrying with it. This is kind of like our blank problems. And we're writing out the blanks,
Oh, yeah.
like something is happening. Okay, so same situation with our
Exponents
cards.
change, or are we not there yet?
What?
Or like the exponents change, this would be like 1/2 to the third to the
Um,
second to the first.
That's binomial and geometric. So we'll probably get to there by Friday. Okay,
The worst.
so 3 cards are chosen with replacement. Okay, so I'm imagining like we do 3 blanks since we got 3 cards.
So
Okay.
with replacement, that's a keyword. What does that mean? Does that mean
Keep
denominator
52.
stays
So,
the
like-
same?
You keep the total.
Right,
52
right.
at the bottom.
I'm also going to be careful and make sure I'm writing notation right because I need to let me erase a little bit. Sorry, this is not very efficient.
Do you have one of those
Probability. What'd you say?
things- Do you have one of those things that you can write
She's
on?
screen
The pads
recording.
that
My
Screen
iPad I
recording.
usually use, but since I'm recording my
like, this
screen.
burger has like that.
Oh, yeah, I know what you're talking about. No, I don't have one of those. That would be useful.
Yes.
Okay. See what I did there?
Mhm.
Probably face card.
Yeah. Face card and face card and face card. Remember this? Is it coming back? Okay. So, I randomly choose a card. What's the probability that it is a face card? Do you remember?
12.
12 out of 52. 12 out of 52. Good. I take that card and I replace it, shuffle the deck. What's the probability the second one is a... I take that card, put it back in the deck, shuffle. What's the probability the third one is? How do I get my final answer? Multiply, hence the multiplication rule. Multiply, multiply. I'm not going to do that. Just whatever that answer is. 3 cards are chosen at random without replacement. So same probability notation. Okay, because the question is still what's the probability they're all face cards. Face card and face card and
Oh,
face card. Thanks, Nikki.
Alright, so it's going to be 12 out of 52.
Okay, so yeah, the
11
first
out of
card being a
51.
face card would be 12 out of 52. Then I'm taking that card, setting it aside. So what am I at now for the second one?
11 out of 52, or 51.
Yes, 11 out of 51. I take that card, set it aside. So what am I down to?
10 out of 50.
10 out of 51. Good. And what should I do to get my final answer? Multiply. Whew. Okay. Last one. If 3 cards are chosen with replacement, what's the probability that highlighted at least one is a face card?
Well, we do 1 minus the probability of
Good. So when you see at least one on these multiplication problems, like we know later comes geometric and binomial where we're doing at least 2 and at least 5 and at least 10. But for these easy multiplication ones, we're doing at least 1. There's a shortcut. We need to do
minus.
the 1 minus the probability that none are face cards. So not a face card and not a face card. My finger's gonna be like sore after this. And not a face card. Okay.
Oh my gosh. This is painful for me. And
I'm
not doing
sorry.
it. Now I
Okay, so the first one we draw it, what's the probability it's not a face card?
40 out of 52.
40 out of 52. Good. The opposite, the complement of it being a face card. We replace it, what's the probability of the next one?
40 out of 52.
Good. And then the last one.
40 out of
And to get our final answer,
50. Subtracted from 1.
multiply them all and subtract from 1. Caught up to you.
I know.
Good job. So multiplication rule, there we go. All right. The first example, were the events independent or not independent?
They were independent.
Not
No, they were independent.
No, they're independent.
Yeah.
Whoever said that.
Okay, why are they independent?
Because they get replaced.
Well, you know,
Because they're
don't
getting
affect each
replaced
other.
every time. So
The
what's the
denominators
definition of
change.
independent in probability?
one event doesn't affect the other one.
Right, one event doesn't affect the other. So the fact that I got a face card on the first wouldn't affect the face card, getting a face card on the second in problem 1.
But in 2.
But in 2, they were not independent because the fact that I got a face card on the first one affected the probability of the second and the third and so on. So speaking of, make sure you know that definition. Independent events is when the occurrence of one does not affect the occurrence of the other. What's disjoint events though?
Isn't that like mutually exclusive?
Yeah, another word for disjoint is mutually exclusive. Those are synonymous. So if you see that, what does it mean?
You can have both of them.
It's not a Venn diagram. They're like two different things.
Yeah, like a Venn diagram, disjoint events would be no overlap. It'd just be two. Can y'all give me an example?
People who get 5s on the AP exam and people who get 4s on the AP exam.
There you go. Okay. So very good. So the event getting a 5 on the AP exam and getting a 4 on the AP exam, those are disjoint because you can't make a 5 and a 4. Okay. So question. Think deeply. Can disjoint events be independent?
They They already are.
Okay, let me rephrase the question. Are disjoint events independent?
No.
Well,
They are.
I don't know. I have a feeling that we wrote this down about Venn diagrams. Something about Venn diagrams.
Aren't they not?
We talked about this before. Okay, that
No, they are. It's like if you use like the AP exam, like my score isn't gonna affect someone else's, and if I get a 4,
Okay.
it's a 5.
Wait a minute.
but the
Like the
event
curve.
is not necessarily what you. The event is getting a 5 and getting. It's not necessarily you. Okay, so let me use that same example to help you with this. So y'all agree that getting a 4 and getting a 5 are independent. Or sorry, are disjoint events. You can't get. There's no outcomes in common. You can't get them both, right?
Yeah.
Okay. So I tell you, thinking about individually, I tell you for sure, Jake got a 5 on the AP exam. What's
No,
the probability
no way.
that he got a 4?
Zero.
So
So they're
was
not
the fact that you knew that Jake made a 5 affect the probability that he made
Yes.
a 4?
Therefore, it's
Yeah.
not
Not
independent.
They're not independent.
Boom.
Very good. Did your mind just get blown?
Yeah.
So the
Oh,
definition of
that's
independent
everyone
events
else
means the fact that I knew something, that something was given to me, some kind of information was given to me, shouldn't affect the probability of the other happening. But I knew you made a 5, so I knew the probability you made a 4 was 0. So they were not independent events. If one happens, I know something about the other. So disjoint events cannot be independent. They cannot occur at the same time. Okay. All right, y'all are good at these. 2A table probabilities. Yes, y'all are good. All right, so I'm glad I left all this stuff from the 7th period. Okay, let's just run through. If a student is chosen at random, what's the probability that the student smokes? So don't forget to define these events, okay? So an easy way to do it is just to go to the table. They have to grade everything that you write. So if you go back up to the table and say S equals, and just do it right beside student smokes, that's okay. Saves you a little bit of time. Or you could write it S equals student smokes, either way. But make sure or you can just write the probability that student smokes in parentheses. Like, you don't have to do the event if you don't want to. Okay? But do some kind of probability notation if they're asking for a probability. Your answer should have the probability notation. All right, so what am I taking this out of?
5, 3, 7, 4.
7, 5.
3. You were
So
so
close.
close, girl. So close. Yes, because it's out of the total, and then what's the top number? 1,004. That's how many smoked in the sample. Good. Done. Or you can do decimal if you like decimals. All right, B, coming down here. I meant number 2. Okay, so if a student is chosen at random, what's the probability that both the student's parents smoke? So I'm going to let that be B. So what is it out of?
5, 3, 7, 5.
Yep, 5, 3, 7, 5. That's Missy. And what's the top number?
1, 7, 8, 0.
So both of the parents smoke. That is 1780. Good. C. If a student is chosen at random, what's the probability the student does not smoke and neither parent smokes? So that's, see how I set it up? D and N. What's it out of?
5, 3, 7, 5.
Y'all agree it's still out of the total?
Yes.
We're still choosing a student at random. And what's the top number?
1,
1,
2,
1, 6.
Yes, this right here. Student doesn't smoke and neither does both parents. So 1168. So when is it when the bottom number is not going to be 537?
No.
Yeah, if I'm given some kind of information ahead of time. Okay, conditional. That's what you're right. So look at number 4. Given that both parents smoke, so I can stop there. What's going to be my bottom number?
1, 7, 8, 0.
Yeah, given that both parents smoke. So now I'm given that this is the only part of the table that I'm looking at. I don't care about the rest because I know for sure it comes from this part right here. Both parents smoke. And then what's the probability that the student smokes. 400. Done. So, sometimes it's better just to use your instinct to do a conditional probability problem, especially if it's coming from a two-way table. Okay? But isn't there a formula for conditional probability? Yes, there is one. And that's what this next slide right here says. It's right here. This is actually on your formula sheet, so don't have to memorize it. Just know it's for conditional probability. Okay? But for these tables, we did a conditional without even worrying about it. Could I have used it? Yes. And it gets confusing. That's why I don't recommend it. So I could do it. I did it right here just to show you. Okay? You would have to do the formula says for S given B. You do S and B over the probability of B, and then you just use your table and then calculate it. So the question is, yes, you can use it. Just be careful and use it right. But sometimes it's just better just to use your own, knowledge. Okay? So when do you use it? Two for sure places, tree diagrams or questions about independence. Okay? We talked about independence not long ago. So that's where I've seen it the most. I mean, there may be other times, but most questions that have tree diagrams and conditional problems and independence. Okay? So speaking of, let's do it. Okay. Let's try this example. Manufacturer of ice cream. This is going to make me want some ice cream. Used 2 machines to fill pint containers of its bestseller, Super Chocolate Almond Fudge. Since each pint is supposed to have 38 almonds, but 25% of the time the older machine will dispense fewer, while this occurs only 10% of the time with the newer machine. 80% of all packages are filled by the newer machine. What proportion of Super Almond Fudge pints contain fewer than 38 almonds? So how do I know that a tree diagram is the best method here? Yeah, to me, there's so much information being thrown at me and it's dying to be organized. Correct? And it's kind of sequential. So, meaning they give us something and then something based off of something. Right. And so this goes to our practice exam. The tennis problem was a tree diagram one. Because you had winning the first set, then winning the second set, that kind of thing. So that's how I know a tree diagram is good. So help me do one. What are my options for my first branch? New machine, old machine, good. And it's, of course, I'm not going to do that, but define your variables.
No point.
What's the probability? Yeah, 80% are filled by the new machine, meaning how many are the old? 20%. Good. So your branches should always add up to 1. So if they use the new machine, what's the probability that it has fewer than 38 almonds? Good. If they use the new machine, 10%. What about 38 or more?
75 or 90.
Right? Our branches got to add up to 1. Now, the old machine, less than 38 almonds.
25.
Good, meaning how many would be more than that?
75.
Wait for it. Wait. Okay. So, there's our tree diagram. Let's answer the question. What proportion of the pints contain fewer than 38 almonds? How many times does this happen on our tree? Twice. Here, they end up with less than 38 almonds. And here. How do I find that probability?
Add it or multiply them and then add.
Yeah, so you can't just jump into the branch, okay, or into the tree. You have to work your way along a branch. Remember that? So to get to this 38, I have to go 0.8 times 0.1. Good. So hold on. The probability, I'm just going to do this, fewer than 38 would be 0.8 times 0.1 plus what?
0.2 times 0.2.
Yes. 0.2 times 0.25. Follow the branch. And whatever that is would be our answer. Okay. So suppose after a difficult exam you reward yourself and purchase a pint of this ice cream and you find that it contains fewer than 38 almonds. What's the probability the container was filled by the older machine?
The probability of fewer than 30 given.
Oh yeah, it's a given problem, right? What are we given? Nope.
No, you're given that it's 30, less than 30.
Good. Your pint had less than 38. What's the probability
That is older.
that it's from the old machine? So what am I going to do?
Probability of old and less than 38 over probability of less than 30.
You got it. Use our formula. The probability that it's old and, that's an and sign, less than 38 divided by the probability that it is less than 38. So where do I find that?
What tree diagram?
Tree diagram. Where's the top?
0.2 times 0.25.
Good. So the top is old and less than 38. So that would be the top. 0.2 times 0.25. I'm not going to write it. Okay. So the old, I'm just going to highlight it, and that would be orange. Follow the orange. What about the bottom? The probability that it's less than 38. That's the blue we did up there. Very good. So that, just refer back to your answer in A. And you got it. What do you think, Jake? Y'all get quiet. All right, number 3. Are the amount of almonds in the ice cream and machine use independent events? How do I figure this out?
No.
How do you figure it out?
Oh, the probability of the
A
given
and B
that-
given it.
Yeah.
Yes, there is a test for this. If you're in the middle of a probability for your response question and they're asking you about independence, please do not do a whole chi-square test for independence. Okay, that is when they're saying, is there sufficient evidence that the amount of almonds and ice cream in the machine you are independent? So, no, be careful with the language there. Okay, they'll try to hopefully prompt you a little bit more if they're wanting you to do an entire test. Okay. Plus, we've already done a lot of work for this one. I don't think they're going to want us to do an entire test at this point, too. So we use our test of independence, which is the probability of A given B is equal to A. And the reason why this is our test of independence, because if these are independent events, it shouldn't matter that what we're given. It shouldn't matter that B occurred. The probability of A should be the same if they're independent. Okay? That's why this formula works. So how do I do that for this problem? Well, I'm not going to do extra work. Why don't I use the answer I found in problem 2? Right? Didn't I already find that probability? Why don't I see if it's equal to what?
Probability of
What's the
old.
good? Which
What
is
would the
0.2, right?
probability-
Yeah, probability of O would just be 0.2, this branch right here. And then whatever you got for your answer in 2, do that. So if they're not equal, which I think happens, it would be not independent. Not equal, not independent. Equal, independent. So in your Frappies tonight, you'll get one of these to practice. Okay? So if that is not on your formula sheet, you'll need to know that. But the thing to remember is that it shouldn't matter what's given, right? Probability of A should be probability of A, no matter what's given. I think we're done with our slideshow. Yay! Can we look at the tennis one? Y'all have the ability or the drive to look at the tennis one? Remember this one?
Yeah.
Okay.
The first one's easy.
Yeah, a lot of you got the first. Okay.
And then we went to
So remember in tennis, best 2 out of 3. So give me the situations where player V wins the match.
VVM.
V.
Oh yeah.
No
Or-
M because best 2 out of 3.
Or VMV.
VMV works. MVV works. Any others? Nope. Okay.
He's awake.
He's awake. Okay, so give me the situation where M wins.
Same thing. Just switch them.
Yeah, just switch the letters.
Good. MM.
Same thing.
MV. Yeah, I don't know if they would take that. And VMM, right? So that didn't even, remember, we want to get as much as we can. That didn't even require any probability. That just required thinking.
That's a struggle.
But you got an E. That was an E. Look at there. Done. Some of y'all just read it and was like, nah.
Too long.
Too much. Now, this part,
So hard.
this part, you got to use your
This
brain.
part's a
It was
probability.
like,
I was like, nope.
they were like, we got to let their brain rest a little bit for part B. Okay, basically, this is setting up a tree diagram.
Oh, I got it so
Yeah,
wrong.
that's what you're supposed to do.
All right, let me help. All right, first set. Either M wins or V wins, correct? What's the first sentence say is the probability?
If I'd done a tree diagram, I would have said what you said.
Equally likely. Actually, that's the second sentence, right? So 50-50.
I was like, how am I supposed to know? Should I add these together? I'm pretty sure I've added them together.
All right, second problem. If V wins the first set. So that was the first set. Now I'm working on the second set. If V wins the first set, the probability that she will win the second set is 0.6.
How many frappies do we have tonight?
So meaning what for the other one? Good. If player V loses the first set, that means M won. The probability that she will lose the second set, meaning M wins again, is 0.7, making the other part 0.3. If player V wins exactly one of the first 2 sets, so that would be here, she won one of them. So if she wins exactly one, the probability she'll win the third is 0.45, meaning the probability she'll lose the third is 0.55. Does that occur somewhere else? Right here, right? So the question is, wait for it. What is the probability that player V will win a match against player M, meaning they win the entire best 2 out of 3? There were how many situations where this happened from part A? 3. So, well, the probability they win, let's find them on our chart here. So, player V wins here. Agreed?
Add those together.
Do I add them together?
No, multiply and then add.
Yeah, 0.5 times 0.3 times 0.45. Right? All right, where else does it happen?
V, and then VMV.
Yeah, VMV. So I would multiply 0.5 times 0.4 times 0.45.
I'd be the fool to do this, but then add them together instead of
Yeah,
multiply.
that's true.
Would you get
I
partial?
multiplied wrong.
I don't know. Probably not.
Oh my god.
They're so hard.
So once you make the Venn diagram, you can see like you can
So much
it's, yeah, but it took a lot of thought to kind of work through that Venn diagram. Or sorry, tree diagram. So you go 0.5 times 0.3 times 0.45 plus 0.5 times 4 times 0.45 plus 0.5 times 0.6. So you multiply as you're going along the branch, but add in between branches. Okay? Here we go. What's the probability that a match between player V and player M will consist of 3 sets? Very important word. Given that player V wins the match. So let's set up the probability that they win 3 given V wins. So what's the formula?
P of 3 and V over
3 and V over the probability that V wins. So where can I get all of this information? Back at the tree. So 3 sets and V wins. Where is that? This one and that one, right? 3 sets. Multiply and add them up. That's the top. And then what about the bottom? The probability of V wins? Guess what? We did that in problem B.
Gee, these are way easier now that we know what we're doing.
Just got to review. That's all. It's coming back. Good. So that's how you were supposed to do C. D. Yeah, there's more. We're almost there. What's the important word? Expected number of sets played when player V competes in a match with player M.
I remember I just wrote 2 for this.
Okay. How many? Okay, first of all, tell me. Okay, the expected number of sets. So what are our possibility of number of sets?
2 or 3.
2 or 3. Okay. In how many situations? Okay, going back up here, wasn't there 6 different situations?
Yeah.
And how many of them did we only do 2 sets?
2.
Oh. And then the
So
remaining
2
4.
out of 6, right?
11.
And then how many were 3 sets?
4.
4 out of 6.
Then
So do you
multiply and
remember,
add
I just set up a
together.
nice little probability distribution. So do you remember how to find expected value?
2 times 2, 6.
2 times 2, 6,
Plus
plus 3 times 4, 6. And it ends up being some kind of decimal.
That would have got me to 3. Number 1.
Yes, you put in list 1, 2, 3. In list 2, 2, 6, 4, 6. And then you can go to 1 var stats, L1, L2. Yep.
I used the probability.
Don't tell me there's an E in there.
Okay.
I got 2.1. I was like,